save them.
Nope.
Only one of them, in my opinion, was different.
Which one?
So 56A.
56A, what is it? Go ahead.
So that's the one where you gave us a complex, or where you gave us it instantly on metal or whatever. And A was, what is the value of R? And B was, derive a relationship to the value of R. Do you want us to just do B first and then do A? Because otherwise you didn't lose any form of, otherwise there's a bunch of relations we have to use to make that actually not.
Was it one of his?
No, it was yours.
One that I wrote?
A plane polarized electromagnetic wave of frequency omega in free space is incident normally on the flat surface of a non-permeable material, U is 1, of conductivity sigma and dielectric constant epsilon. A. Calculate the amplitude and phase of the reflected wave relative to the incident wave, for sigma is a number, epsilon real is a number, and omega is a number. B. Show that for a very good conductor, the reflection coefficient is
Oh,
R
I would do B after I did A.
1 minus 2
Which you were deriving in B for A.
Well, you're along the, as you're going along the path to B,
R is the reflection.
you solve A,
Yeah.
seems to me.
B was general, we didn't even need to do, you don't need.
Was B that general?
B-
I thought
B
B was
had
a
no
specific
numbers.
case.
B was general in that it had,
A delta in it. No, but it had
No.
delta.
but delta didn't need to be a number, it was just the general symbolic case.
Delta is the skim depth, right?
Yeah.
Yeah.
All
So
right.
B was solved for, in the case of a very good conductor.
No, delta can be a number.
It's just,
It
it can be a number, but
Yeah,
In part
I guess
B,
the
you're
way that I
saying
see it is
it's
that part A, I defined the quantity, I defined the terms, but I didn't give you numbers.
You did give us
Say
numbers.
numbers in
You gave us a number for sigma and epsilon and
Oh, I did?
omega.
A. A has
And B.
numbers, B doesn't. That's why I solved B first.
Okay, B is a specific case, though, also, is for a very good conductor. Now, it may happen, but I don't believe, that case A is a very good conductor.
it's a very
So is 1,000,
Is
is 1,300 greater than 1?
Yeah, so it's a very good conductor. Well, I guess that they apply to the same, I didn't intend for them necessarily to be the same case. But then that means that by solving B, you solve A.
good.
Solve B in general and then plug it in. Yeah, so,
So,
so you could do B first, then A.
so,
Yes, you
so
were
it's the
right.
same, they're both very good conductors.
They're both very good conductors. I think when I made the numbers up, I intended for one to be sort of an intermediate case. I intended for A to be not a very good conductor, and I screwed up.
Because you tried to put in 10 to the 11 and 10 to the 10, but as the numbers turned out working out, that ended with 1,000 when we did the division, right?
Yeah, okay.
And
If
so,
you say I did that, then I did that. Yeah.
along with that equation, you have the real part of n. I was just unsure about how you go about finding that you untangle the, how do you deal with the complex number in the square root? What's the best way to deal with that?
Phasers.
Didn't need to if it was a good conductor?
I'm not,
I mean, because n is given in terms of the square root of.
are you're asking how to take a square root of a complex number then? That's the way that I read it.
Yeah.
Okay, and the, let's say, the easy way to do it is to convert that number into a polar notation.
Okay.
And then the e to the I angle becomes half the angle when you square root it.
Okay.
And the real part, you just take the square root.
Okay. Could you draw a picture of that?
Yeah, oh, okay. So I've got A plus IB, and I want to take the square root of that.
Right.
Okay? I could also, that's my complex number. All right? And now I want to take the square root of that. So I can rewrite, this is just one way of doing it. I can rewrite this as a squared plus b squared times e to the I. Now, someone help me here. Arctangent of b over a.
B over A.
Shouldn't it be the square root of a squared plus b squared because it's an equal to?
Yes. Thank you. Okay. Then, when I take the square root,
Okay.
Of course. Well, you could, I mean, you could solve it that way, but if you know it's a good conductor.
yeah, in the case where sigma is much greater than epsilon times.
Right. Can you Taylor expand it?
Yeah.
Oh, okay.
Well, no, you don't even need to do that. If it's much greater, then you actually just take it to be imaginary. So you're taking the square root of I, let's just say times a.
Okay.
You know, whatever the sigma term was,
Right.
right? And that's actually equal to 1 plus I over the square root of 2 times a to the 1/2. Magnitude a to the 1/2. Well, a is real.
Okay.
So that's what Ryan was talking about, the approximation,
Right.
which I did in the notes
Oh, okay.
for a good conductor. Call the notes.
All right.
The videos are going up as we speak.
What?
The videos of that are going up as we speak.
Oh, that! Not these. I thought somehow you found a way to just
Simultaneously.
broadcast me, and that would be
Live percent now.
I can if you want.
No.
I can see the map.
I do not want to do that.
Very cool. So we just go to class in the room. So the next
In the
step's
room you
all-
like, yeah.
Then you can
Actually, I have another question here.
Oh,
Can you talk about 55, so 12.27?
Yeah,
Yeah,
that was the one I thought about. I thought you'd have problems with that.
okay.
So you have actually for any fields, you've got a set of 4 boundary conditions that have got to apply
Right.
for the incident and reflected fields. And I'm going to have to open the book to remember them. Yeah, remember the equation numbers. In chapter 12, it's equations 121 through 124. Okay. So as an example, you have E parallel so the parallel component to the surface plus the parallel, let's call this reflected incident equals the parallel transmitted. Okay, that was one boundary condition that we had. Now, what we're talking about is a wave that's incident on the surface where the electric field is in the plane, perpendicular to the plane of incidence. Okay? So it turns out that this is the whole field is parallel to the interface, all of it. All right? So what this actually ends up really being is that as a relationship that must be obeyed for the fields. Be transmitted, be incident, be reflected. Okay, so I've got one, right? I've got, I'm not sure whether I'm going too far back here, right? There is no field perpendicular to the surface, so the second boundary condition, 122, is not obeyed, right? It actually turns out that the third boundary condition is the same as the first boundary condition, if you work it through. And then you've got the fourth boundary condition, which is that be perpendicular in plus be perpendicular reflected equals be perpendicular transmitted. Okay? And that's going to be, let's see if I want a perpendicular component to the surface, and that looks like that. And this, if this is theta, then it's going to be b cosine theta. All right, so b cos theta incident, let's just call it theta, plus b reflected cosine theta is equal to b transmitted cosine theta prime. Okay? Then b in any medium is equal to n over c times the electric field. Oops. No C? No, no C. Because B and E have got to be the same dimensions, units, magnitudes.
It's talking the magnitude rather than the direction.
No directions here. I'm sorry. How about that? Yeah.
How can you have the, I'm pretty sure you covered this again, but I'm just more curious about the physics behind having the electric field perpendicular to the plane of incidence. So how is that even possible if it's
Simple. No, I have a wave. Let's call this the plane of incidence. This thing. Oh, sorry. Let's call this the reflective surface.
Okay.
No. Let's call this the reflective surface.
Okay.
Here.
Right.
Okay.
Okay.
Now I have a wave coming in like this.
Okay.
That wave that's coming in like so.
Okay.
Could have an electric field that oscillates this way,
Or it can
have an electric field that oscilates
so the
that
plane
way.
of incidence is where the.
So this is the plane of incidence,
Okay.
and perpendicular to the plane of incidence is this
Yeah.
polarization.
Then that's just my bad.
So the electric field is in the plane of the surface.
Okay.
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 It was definitional, I think.
Yeah, that's exactly what it is.
Yeah. Right.
Was it okay?
Did I lose a minus sign? Here, I might have.
That's not the way I did it.
Okay.
Was it okay to just construct the general pointing vector and then know what K was, plug all that stuff in, and then be done?
Yes. It actually turns out that when you do this, right, that you and then you apply it for the case of an imaginary index of an imaginary angle. Right, I'll come to that. Then you end up with a wave propagating along the surface and a wave propagating perpendicular, and something, a field, not yeah, a wave propagating perpendicular to the surface, right? It's actually just decays perpendicular. It's not an oscillating thing, it's not a traveling wave, but the field decays in that direction. Right? What I guess that I did was I wanted to prove to myself that the k vector was in the plane of the surface, that the imaginary component of the traveling wave was in the plane of the surface. So I started from scratch, because although he doesn't mention it, it's, if you start digging through it, Ohanian actually only derived the conditions, the wave for the evanescent wave. You only derived the evanescent wave for p polarization, for polarization in the plane of incidence. I could find no mention in the text that that's what he did, but when he wrote down his boundary conditions, he used boundary conditions on E that applied only to in the plane of incidence. It turns out that derivation, the way that you find K, it is the same for parallel and perpendicular. So I think that it's actually okay to assume that K is along the surface, in which case the Poynting vector is along the surface, okay? I guess there's another, maybe I'll jump to,
I didn't assume K was along the surface. I assumed it was in both directions and then solved for one.
okay. Then what you did was fine. I'm gonna state a result that it would be fine if you started there and continued on. But the result comes from what I started doing here. Setting up boundary conditions and then figuring out what the ratios of the fields have to be in the most general case. All right? So I started from scratch. But another approach would be actually to just take your field ratios from equation 142. So here, I started with equations 121 through 124. I started with the boundary conditions. It would be perfectly fine with me if you started with, in the book, equation 142, which is the field ratio for the incident and the reflected wave. It's the Fresnel coefficient, which has got sines and cosines in it, right? So there's one neat trick which he mentions in the total internal reflection case, which is this. I wanted to write it. So I'm just going to write over here that this is a function of sine of theta, sine of theta prime, cosine theta, cosine theta prime, and they're all related by n and n prime. Okay, I'm just going to say that, which is equation 142. All right? Your problem is that theta is complex. You have the case of n sine theta equals n prime, sine theta prime, and the incident angle is larger than n over n prime times the incident angle is greater than 1. All right? So it's not actually not that that's not solvable for sine theta prime, but sine theta prime, it becomes complex quantity, right? And so, but it's easy to find here, right? We can say sine theta prime itself, or theta prime, it becomes complex. Sine theta prime itself is n over n prime sine theta. And then the other thing that appears in the equation is cosine theta prime. And that one's easy too. Well, not so easy. Theta prime is equal to 1 minus the square root of 1 minus sine theta prime squared. Which then you can get rid of the theta prime by going up here. And then when this is greater than 1, you've got an imaginary quantity here, but who cares? Cos theta prime is something that you just found. It's related to the indices and the incident angle. So you just plug it in. And so you've got a complex quantity for your propagation vector. You stick that into the, so what you find out is that K prime is complex. All right? And when you do that, you end up with a propagation that looks like e to the minus, let's call it cap of z, e to the I, K prime x minus omega t. I have to think about what this quantity is. This is the real part of K prime. There's going to be an index in there. Which is a term that decays in Z and a term that oscillates in X. You know, it's a traveling wave along X. Where X is the plane of the surface. XY is the plane of the surface.
So is there a reflected and transmitted wave, or is it just one or the other?
The amplitude of the reflected wave, far from the surface, is equal to the amplitude of the incident wave. Okay.
Okay.
But actually, some of the incident wave travels along the surface for a little ways and then reflects. It actually, I think Ohanian points this out, it actually behaves if you have an incident wave, let's say, like so, then the reflected wave is observed to come out like that. All right? These two don't coincide with one another. And it behaves as though those two waves intersected at a depth, which corresponds to 1 over kappa here, this term here. So it's like the wave penetrates the surface and comes back out again. You actually see this effect too in quantum mechanical tunneling. That the reflection coefficient is 1. It's all reflected, but the phase is shifted because the wave traveled a little ways into the material before it came back out again. Yeah.
Is this where frustrated transmission
Yes.
come from?
So yeah, in fact, if I now chop this material off so that I have material 1, and material 2, all right, I can actually couple this wave out. And even more, even neater, is that I can have a very well-defined wave here incident on the surface. You know, I've got an aperture. That's it. I'm hitting there. I can put something over here and still couple out. Of course, this wave traveled along the surface and then came out. So I don't even have to be there. And people have done this measurement and observed that that's displaced. The distance by which it's displaced is really tiny. It's of order of wavelength, but it's there.
And you use microwaves or
Yeah.
radio waves.
Professor Schroeder, we'll call this, I think there's an umlaut there, because he likes arcane names, the Guth-Henshin effect. Right? Everyone else calls it frustrated reflection.
again, it begs the question, why do Faraday cages work?
Oh, they're thick enough.
You know?
Yeah.
Even though the wavelength is on the order of, kilometers or something like that. It doesn't-
Ah,
Is it?
yeah, but you have to look at the skin depth because what we're talking about here are materials that do not absorb.
Okay.
All right, we're just talking about a real index of refraction,
Yeah.
giving still a wave that has some depth to it. Okay, but in the metal case, you've got a real. No, sorry, I didn't mean to put it that way. You've got conductivity in the material, which
Right.
leads to an imaginary component
Okay.
to the index of refraction, a dominant imaginary component,
Okay.
right? Which means that the skin depth is really small. And if you work it out for, let's say, radio waves on a sheet of metal,
Yeah.
I think that you'll end up finding out that the skin depth, let's see, the frequency is low. The skin depth is going to be like a millimeter. It's really small
So what we've been doing
compared
is
to the wavelength.
perfectly transparent, on metals currently. Transparent steel in Star Wars.
What we've been doing here was we assumed that the index was real.
Transparent.
Yeah, but not a metal.
So does that mean it's physically impossible?
So it's a dielectric. Glass.
But the other times we do metals, we've been assuming the,
Now with metals, we've been assuming that there's conductivity, but no other absorption processes, all right? Which if the actual optical properties of metals were due to conductivity, but no other processes, all metals would look silvery, all right? But gold and copper clearly don't. And that's because we have interband excitations that can occur in gold and copper. So there are other absorption mechanisms besides conductivity.
Now, what does this mean for, let's say, superconductors that do not allow any, what I would imagine, penetration of electric fields or magnetic fields?
They reflect really well.
I'm just thinking because to me, it feels like they just, like all the waves just circle around and it'd be visible.
Would it bend?
No, they reflect.
They reflect.
and magnetic fields that are in there when it turns.
They'll still be there, they're captured.
They're pinning, flux pinning, it's called.
Or rather, no, they're excluded.
But then you can get flux pinning also in magnetic field. That's why you've got the cool things where it's floating upside down.
Yeah.
You ever seen one of those tracks?
Yeah.
Because the magnetic field is pinned into the, it's pinned against.
Oh, so coming back here, I have one more way that would be acceptable. Here. So the other is to start with that, and then work your way through from there. And then, no, actually, this is not acceptable. This is a stage that you would find your way to. So I'm telling you what the answer is going to look like. Transmitted field is going to look like this. That's some constant which you can deduce. Right? E to the I K X minus omega t, for example, in the y direction, because the plane of incidence is xz, and so the field's in the y direction. Okay, so this would be my transmitted field. It's got something that decays perpendicular to the surface and propagates along the surface. And then the magnetic field through the transmitted way has that magnitude. I probably have got a C in there as well. C over omega, all right? E to the minus kappa z. But now, so that's times kappa sine, oops, e to the I, kx minus omega t, x plus magnitude of k prime, I think, e to the I